I'm going to finish up this set of slides about atoms and isotopes and some early atomic theory. So as you recall, let me back up. We looked at atoms and ions, and we went through how to determine the number of protons, neutrons, and electrons, right? And then I just summarize an atom, the smallest piece of an element, has no net charge. For ions, there's positives and negatives. Remember, always do the protons first. So positive ions have more positive, therefore fewer electrons. Negative ions have more negative, so extra electrons. And I showed you here that here's an example of potassium and potassium ion. This is potassium, the metal. This is the ion. You can see their physical properties are very different, right? Changing only the number of electrons. And I showed you this video just to demonstrate the chemical properties are also very different. So bottom line is if you change the number of electrons, the properties change significantly. Now, isotopes are defined as, I actually have written down what an isotope is, yes. These are isotopes. So this is phosphorus and phosphorus-32. Both of them are phosphorus, and again, look at your periodic table, 15 protons. This one has 15 neutrons, this one has 17, and they both have 15 electrons. So these differ only in the number of neutrons, and these are isotopes. Isotopes are atoms of the same element with different numbers of neutrons. So Dalton was wrong about atoms of the same type being exactly the same, but he just didn't know about isotopes. Right? Now, what's interesting about isotopes is isotopes have nearly identical properties. Nearly identical. There's no cool bits because the properties are basically the same. They differ in mass and density, and then sometimes radioactivity. And again, we're not going to do a unit on it, but just to briefly talk about it, radioactivity is when an atom falls apart and it gives off lots of energy. Since the other properties are similar, it can do the same reaction. So you could do a reaction that regular phosphorus will do. This is a radioactive isotope, and this one is radioactive. It'll do exactly the same reactions. And so, for example, DNA contains a lot of phosphorus. You can make DNA with radioactive phosphorus. Why would you want to do that? Well, I can find it because I can detect the radiation. So I could follow a piece of DNA simply by making it with a radioactive isotope, and I can see where it goes. And we take advantage of this a lot of times in the sciences. It's a means to follow processes, tracers, and again, radioactivity in terms of energy. Very interesting conversation. Just not something, that we're going to do in this class. All right, but just suffice it to say that the elements behave almost identical. All right, so just to summarize, isotopes, same element, different mass. If the mass is the same, but if the mass is different but the element's the same, what's different structurally? Well, if the element's the same number of protons, therefore what must be different is the number of neutrons. If you change the neutrons, the properties don't change very much. They have very similar properties. Ions are charged. They have very different properties. And structurally, what's different between an atom and an ion? And that is the number of electrons. So interestingly, if you change the number of neutrons, not a big deal in terms of the properties of the element. To change the number of electrons makes a big, big difference. All right, and I just talked about that, so we're not going to go into it because I just said what's on this slide, okay? Right there, all right? So that's just something that you'll see as we progress when we look at more about the structure of the atom, all right? Now, atomic mass, if you look at, again, looking at a periodic table, this is a better one. You can see that there's the number missing here, but you can see these are the atomic numbers. These numbers down here are still a little grainy. These are atomic masses. Now, if you remember, protons and neutrons have masses of 1. So why are these masses not whole numbers? And some of them are close, like 4.02, 1.008, 6.9. But then you have some like chlorine, 35.45. Right? Or copper, 63.5. I know they're hard to read, but if you have your periodic table, you can read them. Okay? So what's interesting is, well, why would they not have, whole number masses if they're made of things that have whole number masses? And the answer is atomic masses are averages of the masses of the isotopes. Right? They're the averages of the masses of the isotopes. Now, when we calculate an average, it's not the way you were taught. You add up all the things and then you divide by the number of values. That's one way to do it. Another way is to take the percentage of each thing, percent of A and the value of A, percent of B the value of B, percent of C the value of C. So for isotopes, the atomic mass would be the percent of isotope A times the mass of isotope A, and the percent of isotope B, mass of isotope B, and so on. Now, why do we do this? Why do we care about the mass so much? Chemistry has a real problem, and that problem is we want to know how many atoms are in a sample. But we can't count atoms because atoms are too small to see and too numerous to count. So what do? Well, think about when you were a little kid and maybe you went to a place like Chuck E. Cheese and you got all those tickets before they had barcodes. They would count by weighing, all right? So that's something we're going to deal with later on when we get to the slides on the mole concept, which will be some material that's on exam 2. The next slide, I'm not going to click on this. You can do this yourself. I'm not going to do this during my video. But this is a video of this data, or you can click on this. But it's 3.5 minutes long, so I'll let you watch this on your own. But in this video, what I did is I had paper clipium. I call it paper clipium. And so I have paper clips. That's similar to isotopes. Same thing, different size. So large paper clips, right? I'll call them PCl. Small paper clips, PCS. Again, watch the video. It's pretty cool. It's a little cheesy because I'm doing it with one hand and filming it with the other, but still. And so I have a sample that had 35% large and 65% small. I put each one on a balance, and the large weighed 0.96 grams, the small weighed 0.42. So again, if you go back to the previous slide, percent of A times A, percent of B times B, right? So the average would be the percent of the large times the mass of the large, percent of the small times the mass of the small. Plugging the numbers in, 0.35 times 0.96 plus 0.65 times 0.42, right? That comes out to be 0.61 grams, so that the average paper clip would weigh 0.61 grams. Now, what use is that average? Again, if you watch the video, there is no paper clip with a mass of 0.61, but we can count by weighing. And so what I also do in here, again, watch the video. And if that doesn't load up well, it's on YouTube as well. All right. But I took the handful of paper clips, put them on the balance that weighed 12.58 grams. And if you do the math, if I say one paper clip is 0.61 grams, it comes out to be about 20.6, or just say 20. So 21, 20, 19. And I counted them out, and there were 20 paper clips. So it's a good video. Watch through that. But you can see, even in a small sample, we can count by weighing. You wouldn't count a small sample by weighing, but a big one you would. All right, just to give you a couple more problems, and there's a handout on this. All right, so I put the handout in the Canvas shell, but this is literally cut from the handout. So just walking you through just a couple isotope problems, and there's stuff like this on homework 3. So sulfur, and these are made up. Sulfur has 2 isotopes, 32 and a 35. The 32 is 98%, the 35 is 2%. What's the atomic mass? Atomic mass is the average. So the mass of sulfur would be the percent of the 35 times the mass of the 35, percent of the 32 times the mass of the 32. So the percent of the 32, right? The mass of the 32 is 32, the percent of 35, putting them in decimal, substituting it in, and then doing the math, we get 32.06. Right? So you need to know this equation. One more, just doing it backwards. So let's say that you know the average, and don't worry about the unit here, we'll get to that later. Let's say you know the average, right? And you know what the isotopes, but you don't know the percentage of each. Just working the same problem backwards. So again, the mass is the percent times the mass plus the percent times the mass of the various isotopes. We'll use the isotopic mass, 32 for the 32, 30 for the 30. Now we don't know the percentages, but if the P32 is some of it, then the P30 is the rest of it, right? So the sum of the percentages has to be equal to 100% or 1. So if this is some of it, that's the rest of it. Right? So x plus 1 minus x equals 1. So if we put these into this equation, the mass is 30.97 like that. I got off the periodic table. For the P32, the percentage is going to be x, and the mass is 32. For the P30, the percentage is 1 minus x, and the mass is 30. And then it's algebra, right? So 32x plus 30 minus 30x, then 30, and I subtracted 30 from each side, I'm sorry, and then I have 32 minus 30x, so 0.97, I'm rounding to 2 sig figs, right, or 2 decimal places, 2x, and those are the percentages. So there's some problems like this. This is the last slide. There's some problems like that on homework 3. The test will go to there, right? So that's as far as the test goes. The test will cover homeworks 1, 2, and 3. It's a lot of material. That's the first exam. All right, I'm always available on Zoom if you have questions about this, and have a good one.